Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I am studying in CSC AIML, that is Computer Science and Engineering, with a specification of Artificial Intelligence and Machine Learning, second semester, Institute of Aeronautical Engineering. In this AAT Tech Talk of the subject of Differential Equations and Vector Calculus, which has an abbreviation of DEVC, I am going to discuss about the topic of homogeneous equations in physics. First of all, I would like to go through the contents which I have in this presentation of mine. In the first place, I am going to introduce the topic in a very basic manner, and after that I am going to explain about the definition of homogeneous equations, and after that I would like to explain about the first order homogeneous differential equations, and after that I would like to explain about second order homogeneous differential equations, and after that I would like to discuss about what such kind of homogeneous equations have their applications in physics, and after that I would like to explain about the kind of homogeneous equations in vector calculus, and finally after that I am concluding the topic. So these are the contents of this presentation of mine. So first of all, let's go through the introduction of this concept of homogeneous equations. Homogeneous equations are very crucial in the concepts of the subjects like mathematics, calculus, differentiations, integrations, physics, and all that, because they describe a lot of systems, a lot of data, a lot of numerical calculations with a lot of proportional responses. And these kind of homogeneous equations often appear in differential equations and vector calculus. So this is the introduction I've given to you just now. And now let's go through how can such kind of homogeneous equations be defined. Any differential equation can be a homogeneous equation only and only if it can be written in a form where all terms are proportional to the dependent variable or any of its derivatives or all of its derivatives, whatever. So this is the simple basic definition of homogeneous equations and the concept of it. And now let's discuss about first order homogeneous differential equations. The first point I would like to state is that a first order homogeneous differential equation has the form dy by dx is equal to f of y by x, in which f is basically a function of the term y by x. It can be solved by using the substitution of v is equal to y by x, and by substituting v is equal to y by x we can rewrite y as vx, and after that we can differentiate both of the sides with respect to x by giving dy by dx is equal to v plus x of dv by dx, and by substituting this equation into the original equation we can transform it into a separable differential equation in very simple terms of v and x, and by doing this we can make it even much easier to solve. And after that, if we treat v as a function of x, by solving v of x we can substitute v is equal to y by x back in the equation we had first to obtain the general solution only and only in terms of y and x. So this is the information about first order differential equations or first order homogeneous differential equations I wanted to share to you. So now let's go to the second order homogeneous differential equations. And now coming to second order homogeneous differential equations. Second order homogeneous equation theoretically has a general form of a of d square y by dx square plus b of dy by dx plus cy is equal to 0, and their solutions depend on characteristic equations which we use in this concept. A characteristic equation is typically a quadratic equation of the form of ar square plus br plus c, which is obtained by assuming the solution of the form of y is equal to e to the power of rx, and the nature of the roots obtained of the characteristic equation, be it the roots real, distinct, real and equal, or complex conjugates, it determines the form of general solution. So this is the concept of second order homogeneous equations I wanted to share to you. Now let's go through the next slide. And now let's discuss about what the concept of homogeneous equations can have applications in physics. The first one I would like to discuss about is electrical circuits or LC circuits, whatever we refer to. The concept of electricity itself has a lot of theoretical formulae in which the concept of calculus is included. If we include the concept of homogeneous equations, we can be even more efficient in the dealing with the electricity, the electric circuits, and all that. And the next one I would like to discuss about is harmonic oscillators. In harmonic oscillators, we have a lot of theoretical formulas, just like theoretical formulas of electricity in the concept of electric circuits, and the concept of homogeneous equations can also be applied in the same way in the concept of harmonic oscillators. And coming to heat conduction, in heat conduction, the concept of homogeneous equations is very efficiently applied in order to make it even more useful and helpful. And after that, there are a lot of wave equations in the concept of electromagnetism, mechanics, and all that. In such kind of wave equations, if homogeneous equations are applied, we can solve such kind of equations even more efficiently in order to get the solution and make a use of it. So these are a few of such applications of homogeneous equations in the concept of the subject of physics. So let's go to the next slide. And now let's go through the concept of homogeneous equations in vector calculus. I would like to simply state about this that vector fields often satisfy homogeneous differential equations such as in Maxwell's equations, fluid dynamics, electrokinematics, and all that. In this concept, homogeneous equations can be even more efficiently applied in order to be made use of. So this is the information about the applications of homogeneous equations in vector calculus I wanted to discuss about. And finally, I would like to conclude this topic by stating that homogeneous differential equations definitely play a fundamental role in the concept of physics, providing solutions to many natural and engineered systems. So, finally, this is the conclusion of this topic of homogeneous equations in physics. And finally, I would like to thank the respected professors who had given me this wonderful opportunity to speak on about this topic in this Tech Talk session. Thank you.